In this video, we'll talk about the chain rule. The chain rule will be the last of the basic differentiation rules that we learn, and once we have that, we'll be able to differentiate basically any function that we encounter. The chain rule is used to differentiate a composition of functions. Now, what do we mean by a composition? If f and g are functions such that the range of g is in the domain of f, then the composition of f with g, which we write f circle g in this way, is defined by the formula f circle g at x is equal to f evaluated at g at x. It's important that the range of g is in the domain of f, because we start by taking an x, which is in the domain of g, and we plug x into g and get some number out. That number that we get out is in the range of g, and we want that to make sense as an input for f. So the outputs for g must be inputs for f. That is to say, the range of g must be in the domain of f. As an example, let's look at h at x equals cosine of e to the x. In this case, h at x is a composition, f composed with g, where g at x is equal to e to the x, and f at u is equal to cosine of u. So in this case, we're thinking of u being equal to g at x. So u is equal to e to the x. We commonly refer to f as the outside function because it's outside of the parentheses, and g as the inside function because g is inside of the parentheses. The chain rule is a rule for differentiating compositions, and it says that if g is differentiable at x and f is differentiable at g at x, then the composition f circle g is differentiable at x, and this is how we compute it. The derivative of the composition of f with g at x is f prime evaluated at g at x times g prime of x. We often say this as the derivative of the composition is the derivative of the outside times the derivative of the inside. Because we're thinking of f as the outside function, and here it's the derivative of the outside function, times the derivative of the inside function, which is g. Notice that the function g, which starts out as inside of f, is still inside at the end of the computation, but it's now inside f prime instead of f. When we say that g is inside of f, we're referring to the definition of the composition. So if we just go back to the previous slide, this is what we mean. This is the composition of f with g, and g is inside of f. And then if you differentiate that, you end up with g, which was inside of f, now inside of f prime. So it was the inside function, and it still is. It's still inside of f prime. So that's important to remember, that whatever is the inside function stays inside. But then you just multiply by the derivative of that inside function. So why is the chain rule true? Well, we can look at the proof. This is really just a sketch of the proof because we're going to leave out a few of the details. So we start off with the derivative of the composition, and we look at the limit definition. It's the limit as h goes to 0 of the composition at x plus h minus the composition evaluated at x, and then of course that divided by h. But the composition f circle g is really just f evaluated at g at the input x plus h, so this is g at x plus h. And f circle g at x is really just f evaluated at g at x, and of course this is still divided by h. Now we just simply rewrite this using one of our usual tricks. We multiply and divide by something. Notice that the numerator here is the same as it was before, and the denominator h is now just over here. Let's just color code some of this. So we have this f composed with g at x plus h and x, and that corresponds to this numerator, and the denominator here corresponds to this h. But what we've done is we've multiplied and divided by the same thing. So here we have g at x plus h minus g at x, and here we have the same thing but in the denominator. So those two terms would cancel to give us back what we started, but we don't want to cancel them, we're introducing them. And why are we doing that? Well, basically, if you look at this term on the right, this is g at x plus h minus g over h. This is a difference quotient. This quantity right here, this is going to go to the derivative of g at x, which of course is part of the chain rule. This is the derivative of the outside. And we're multiplying it by this quantity here. Well, what does that go to? Well, let's just rewrite it a little bit. Let's let k be equal to g at x plus h minus g. Now, what is that? That's just the denominator here. We're just letting k be equal to this denominator, the difference between the g values at x plus h and x. So that just puts a k right here. So this is now just k. But notice how that changes something in the numerator. Here in the numerator we have a g evaluated at x plus h, but g evaluated at x plus h is k plus g at x. So if you just add this g at x to both sides, you'll end up with k plus g at x is equal to g at x plus h. In other words, if you increment x by a small amount, then you're getting the same value as you were before, g at x, but you're incrementing that as well. So if you increment the input, then that's going to change the output. So you're going to have g at x plus something. Now, we don't know what that is. It's just the difference between these two output values. So the denominator becomes k, but also in the numerator, we replace this g at x plus h with g at x plus k. So if we just color code this as well, we're looking at this term right here, and that's this term right here, which we get from this. Okay, so why did we go about doing that? Well, as we commented on, the term on the right is the difference quotient for g, so it just goes to g prime of x. But what about this on the left? Notice that this is the difference of the outputs divided by the difference of the inputs. And the inputs have a difference of k. And the outputs are f at some value plus k minus f at that value. So you could think of this as f at u. We could think of this as some value u, and this is f at u plus k. And we're looking at the limit as h goes to 0, but if h goes to 0, then by continuity, this thing goes to 0, so k goes to 0. Remember that if a function is differentiable, it must be continuous. So we're assuming that g is differentiable. We're assuming that the derivative exists. And so what does that tell us? That tells us it must be continuous. So as h goes to 0, g at x plus h goes to g at x. So that means that this value for k goes to 0. So as h goes to 0, k goes to 0. So this is the limit as k goes to 0 of a difference quotient. And this is the difference quotient for f, but it's the difference quotient for f evaluated not at x, it's evaluated at g at x. So you end up with f prime at g at x. There's the g at x right there and right there. So g at x, g at x, g at x. And that's why you end up with the derivative of the outside evaluated at g at x. So that's the chain rule. Now the best way to get the hang of the chain rule is by doing examples. So let's go ahead and do some examples. We'll start with the derivative with respect to x of e to the sine of x. Now basically here we need to identify the outside and the inside functions. So when we say it's inside, we're talking about inside the exponent. So the outside function is e to the something, and the inside function is the thing that's inside those parentheses. It's sine of x. So the derivative of e to the something is going to just be e to that thing again. It's going to be e to that thing again. But then we need to multiply by the derivative of whatever's inside there. And what is inside there? Well, that's our inside function. So that's inside the parentheses. So it's going to end up down here. So remember that if you differentiate e to the something, you just get e to that thing back again. But now we have to multiply by the derivative of whatever's inside those parentheses because of the chain rule. But we know what the derivative of sine x is. It's cosine of x. So this quantity right here is cosine of x. So we end up with e to the sine of x times cosine of x. And that's the derivative of our composition. Let's do another example. The derivative with respect to x of cosine of x squared. So in this case, the inside function is x squared. Notice that it's inside the cosine, it's inside the parentheses. So our outside function is cosine of something. And our inside function is that something. It's x squared. So if you want to compute the derivative of this composition, that's going to be the derivative of the outside, but the derivative of cosine is the opposite of sine. So it's the opposite of sine of whatever goes in here, times the derivative with respect to x of whatever went inside. Now the thing inside, this thing inside, that's your inside function x squared. So this is going to be equal to the opposite of sine of x squared times the derivative with respect to x of x squared. And now we have the derivative of x squared, which we can compute using the power rule. So that's 2x. So we're going to end up with the derivative of cosine of x squared is the derivative of cosine, which is the opposite of sine, evaluated at x squared, times 2x, the derivative of the inside. So once again, notice that we still have the inside function inside. We started with x squared inside of cosine, and we end up with x squared inside the derivative of cosine. The derivative of cosine is the opposite of sine, but the thing that was inside cosine is still inside, it's just inside the derivative. But then we have to multiply by the derivative of whatever was inside, and the thing inside is x squared, so its derivative is 2x. Let's do another example. The derivative of the square root of 1 plus x to the 4. And so now when we're looking for an inside function, we mean inside the radical, 1 plus x to the 4. So that's our inside function. So our outside function is the square root function of whatever. And the inside function is whatever takes the role of these dots, which in this case is 1 plus x to the 4. Now we may wish to rewrite our outside function as something to the 1/2 because we want it to look like something to a power because we know how to differentiate something to a power. So in fact, this is the derivative with respect to x of 1 plus x to the 4 raised to the 1/2. And this is nice because now we can see that 1 plus x to the 4 is actually inside parentheses, and that's very often the case. So this is going to be the derivative of the outside times the derivative of the inside. The outside function is something raised to the 1/2. So if you differentiate that, it's going to be 1/2 times that thing raised to the minus 1/2. And we're going to multiply that by the derivative with respect to x of whatever was inside there. Now the thing that was inside there is 1 plus x to the 4, so you just put that inside. But notice we started with something to the 1/2, and we differentiate that using the power rule. So that 1/2 comes down in front, and then we decrease the exponent by 1. So 1/2 minus 1 is a minus 1/2. Okay, so we just need to insert 1 plus x to the 4 inside. So it's 1/2 times 1 plus x to the 4 raised to the minus 1/2 times the derivative with respect to x of 1 plus x to the 4. So we can see that the thing that was inside is still inside, 1 plus x to the 4. Now the term out here, we don't do anything with that. We're done with this part. The only thing we have to do is differentiate this part. And that we can do, again, using the power rule. This is a polynomial, 1 plus x to the 4, so we just differentiate it piece by piece. The derivative of 1 is 0, plus the derivative of x to the 4 is going to be 4x cubed. So once again, you're differentiating using the power rule. The 4 comes down here, and then you decrease the exponent by 1. So you decrease the 4 by 1 to get 3. So just to make sure it's clear that that's a 4, let's connect that up. Okay. So now just putting all of this together, we have that the derivative is 1/2 times 1 plus x to the 4 raised to the minus 1/2 times 4x cubed. And that's our answer. Now you can simplify this if you like, because you might notice that here there's a 4 and there's a 2 in the denominator. You can also rewrite this to a positive power if you want to. You don't have to, but this is 2x cubed divided by the square root of 1 plus x to the 4. And notice that the thing that was the inside function, 1 plus x to the 4, is still inside. It's just inside this power function, which is raised to the minus 1/2. So again, this minus 1/2 is this power 1/2 minus 1. That's where this one comes from. And this power here, x to the 3, that comes from this term. We're differentiating x to the 4 comes down, and then you decrease the exponent by 1 to get 3. That's where this term comes from. Let's do another example. Here we have the derivative with respect to x of 1 over x cubed plus 1. Now the thing that's inside this function is the thing inside the denominator, which is x cubed plus 1. Now another way you can think about this is as a rational function. You could compute the derivative using the quotient rule. But if you don't want to use the quotient rule, you can use the chain rule, because we can think of this as a composition where the outside function is 1 over something, and the inside function is x cubed plus 1. Now, another way to write this, actually, would be the derivative with respect to x of x cubed plus 1 raised to the negative power. And if you write it that way, it becomes apparent that the inside function is the thing inside the parentheses, and the outside function is something to the negative 1. So we can write that down. The outside function is something to the negative 1, which of course is 1 over something as well. But it's just a little bit easier to differentiate it if you write it as something to a power, because then you can just use the power rule. Now the inside function is the thing that's inside those parentheses, x cubed plus 1. So now we want to differentiate this, and by the chain rule we differentiate the outside first. So we're differentiating something to the negative 1. So we use the power rule, the minus 1 comes down. So you're going to have minus 1 times whatever goes inside, and then you decrease the exponent by 1. So then it's to the minus 2. And then you differentiate that, or rather, then you multiply that by the derivative of whatever's inside. And the thing that's inside is x cubed plus 1. So that just goes right in here and in here. So you'll end up with minus, let's just write that as minus instead of minus 1. So it's minus x cubed plus 1 raised to the negative 2 times the derivative with respect to x of whatever goes inside, which is x cubed plus 1. And once again, this is just a polynomial, so you can differentiate it term by term, and then you'll have 3x squared plus 0. The derivative of 1 is 0. So what do we end up with? We end up with the opposite of x cubed plus 1 to the negative 2 times 3x squared. And again, if we want, we can write this as something to a positive power, so we can write it in the denominator, and then we'll end up with the opposite of 3x squared divided by x cubed plus 1 raised to the squared power. If you use the quotient rule, you'll end up with the same thing, and notice what's in the denominator. The denominator is the bottom squared. The bottom is x cubed plus 1, and we ended up with x cubed plus 1 quantity squared. Remember, with the quotient rule, you end up dividing by the bottom squared, and this is exactly why. Because if you write it as something to the negative 1, when you use the power rule, that negative 1 decreases by 1 to become a negative 2. And that negative 2 is why you have something squared in the denominator. Let's do another example. The derivative with respect to x of tangent of x divided by x squared plus 1. Once again, you could do this using the quotient rule, because we have a quotient here. But if you don't want to do the quotient rule, you can always write a quotient as a product. So we can write this as the derivative with respect to x of tangent of x times x squared plus 1 to the negative 1. So you can always write whatever's in the denominator as something raised to the negative 1. So you can always turn any quotient into a product where you have a composition. So in order to compute this derivative, we're going to need to use the chain rule. But we ultimately have a product here, so we're going to have to use the product rule too. So if you want to convert a quotient into a product, you have to use the product rule and also the chain rule. So let's go ahead and do that. So we're going to use the product rule. So it's the derivative of the first. So it's the derivative of tangent times x, or excuse me, it's the derivative of tangent at x times x squared plus 1 to the negative 1 plus the first times the derivative of the second. So the derivative of the second is the derivative of x squared plus 1 to the negative 1. And it's this term here that we use the chain rule on. So let's go back to the start here. We still have to compute that derivative, but we know the derivative of tangent. It's secant x quantity squared. So what do we have? We have secant of x quantity squared times x squared plus 1 raised to the negative 1. Maybe let's just put brackets around this just to keep it all together. Plus tangent of x times, and now we need to use the chain rule to compute the derivative of x squared plus 1 raised to the negative 1. And let's identify the inside function. It's x squared plus 1. This is the same kind of calculation we did in the last example. So we have to do the derivative of the outside. So it's something raised to the negative 1. So we have here, let's just change the color again. We have this term right here. This is something raised to the negative 1. So if you want to differentiate that, you bring the negative 1 down times that thing, whatever goes in there, raised to the negative 2. And then you have to multiply that by the derivative with respect to x of whatever was inside there. But we know what's inside there. Let's just change back to blue. So we know what's inside there. It's x squared plus 1. X squared plus 1. So in the middle of this product rule, we have to do the chain rule. So we're doing a product rule here. But in the middle of this product rule, we have the derivative of something to the negative 1. So you differentiate something to the negative 1 using the chain rule, and the minus 1 comes down, and then you decrease the exponent by 1 to get a negative 2, but then you have to multiply by the derivative of whatever's inside. And the derivative of whatever's inside is the derivative of x squared plus 1, because x squared plus 1 is the thing inside. Now we can differentiate this because this is a polynomial. The derivative of x squared plus 1, that's just going to be 2x plus 0. So now we can put all of this together, and we're going to have secant of x quantity squared, let's write it like that, times x squared plus 1 to the negative 1 plus tangent of x times, and let's put all of this together, we're going to have minus x squared plus 1 to the negative 2 times 2x plus 0, but we'll just write that as 2x. Now, if you want, you can simplify this a little bit. You can write this as secant x quantity squared, and then we can just put the negative exponent in the denominator, so this becomes x squared plus 1. Well, we don't need a parenthesis there. And then from this, we're going to subtract. We subtract because there is a minus sign right there, so we're just subtracting that. And then we're going to have 2x times tangent of x, and all of this is divided by x squared plus 1 quantity squared. And notice what's in the denominator here is x squared plus 1 quantity squared, which is the bottom squared. Here we just have an x squared plus 1, so what we could do is we could give these a common denominator by multiplying by x squared plus 1 in the numerator and the denominator. And what would we have then if we did that? We'd end up with secant x squared, and then we're going to multiply that by x squared plus 1, and that will give us a denominator of x squared plus 1 quantity squared, and then we're going to combine these two, so we'll just have minus 2x tangent x, and we're going to divide all of this by the common denominator, which is x squared plus 1 quantity squared. And notice what we now have. We have the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. So this is exactly the same result that you would get using the quotient rule. Let's look at another example. Now, this example is a little bit more intricate because we have a composition of a composition. So we have our inside function is 1 plus sine of x to the 5, but notice that sine of x to the 5 is also a composition. But let's not think of that right now. Let's just ask ourselves, what is the inside function? And the inside function at this point is 1 plus sine of x to the 5. So our outside function, or our outermost function if you want, outside function is the square root of something, which of course we can write as something to the 1/2. And then our inside function is going to be the thing underneath the radical. So it's 1 plus sine of x to the 5. So if we want to compute this derivative, we just go about doing it the same way as before. So I'm just going to write the outside function as something to the 1/2. So this is going to be equal to 1 plus sine x to the 5, and that quantity is raised to the 1/2 power. So my inside function is all of that right there. So I'm just going to ignore what the actual value is for the moment, and I'm just going to treat it as the inside function. So I have something to the 1/2. If I differentiate something to the 1/2, I use the power rule. So that's going to be 1/2 times that something raised to the minus 1/2, decrease the exponent by 1. And then I'm going to multiply that by the derivative of whatever's inside there. Now, what is inside there is this 1 plus sine of x to the 5. So I just take whatever's inside, and I just put it into these blanks. So this is going to be 1 plus sine of x to the 5th, and I'm just going to put that here too. 1 plus sine of x to the 5th, like so. So now, this term right here, we're done with this one. But now we have to differentiate this one, but in order to do that, we're actually going to have to use the chain rule. Because, well, why? Well, we can first differentiate it term by term. So this is 1/2, times 1 plus sine, and again, we're done with this term. We just leave it as it is, to the minus 1/2. And now we're looking at the derivative of 1 is 0 plus the derivative with respect to x of sine of x to the 5. And now here we have another composition. Our inside function is x to the 5 now. And our outside function is sine. So outside is sine of whatever, and our inside function is x to the 5. So now we can just use the chain rule on this term. So if you use the chain rule, you're going to end up with the derivative of sine is cosine times the derivative of whatever's inside. But now the thing inside is x to the 5th. So the thing that was inside is x to the 5th, but it's still inside, and we just compute the derivative. But what is the derivative of x to the 5? We can use the power rule, that's 5x to the 4. So now we can put all this together, we chain it all together, and we're going to have 1/2 times 1 plus sine x to the 5 to the negative 1/2 times cosine of x to the 5. So we're multiplying by that, and then we're multiplying by 5x to the 4. So this is why it's called the chain rule, because you differentiate the first function, the outermost function, and then you multiply by the derivative of the thing that's inside next, and then you multiply by the derivative of the thing that's inside that. So our outermost function was this square root function, so something raised to the 1/2. So you differentiate the thing that's raised to the 1/2 using the power rule, and then you multiply by the derivative of what's inside there, which is cosine of x to the 5th. But then you have to multiply by the derivative of the thing inside there, which is 5 times x to the 4. So you just multiply by derivative, by derivative, by derivative until you run out of inside functions. And that's why it's called the chain rule, because you sort of think of chaining these all together. Let's do another example where we have multiple composition. So here we have cosine of e to the 1 over x. So in this case, our outermost function is cosine, and our first inside function is e to the 1 over x. So outside is cosine of something, and inside we have e to the 1 over x, which notice itself is a composition. Let me just rewrite this so it's a little bit, so it's e to the 1 over x, like so. Okay, so let's approach this the way that we always do. It's the derivative of the outside times the derivative of the inside. Well, the derivative of cosine is the opposite of sine, of whatever, times the derivative with respect to x of whatever goes inside. So we start with our outside function is cosine of something. So the derivative of cosine of something is the opposite of sine of that same thing. But then you have to multiply by the derivative of whatever was inside here. Now what was inside there? It was e to the 1 over x. So this is e to the 1 over x, and this is e to the 1 over x. So the thing that was inside is still inside, and then we just have to multiply by the derivative of whatever's inside. So now we have a new outside and inside function. The outside function is e to the whatever, and our inside function is 1 over x, which you might rather write x to the negative 1. So now we have the opposite of sine of e to the 1 over x, and we're going to multiply this by the derivative of e to the something. Well, the derivative of e to the something is e to that thing again, and then we're going to multiply that by the derivative with respect to x of whatever's inside. Well, what is inside? The inside function is 1 over x, or x to the negative 1. So let's just put x to the negative 1 here, x to the negative 1 there. So that's our inside function. And this is x to a power, so we know how to differentiate this. It's minus x to the minus 2. Or if you prefer, that's minus 1 over x squared. But let's just write this as minus sine, or the opposite of sine, of e to the 1 over x times e to the x to the minus 1 times minus x to the negative 2. And now we can simplify this. We might notice that there's a minus sign here and a minus sign here, so those will cancel. And now we just write everything with a negative exponent as something in a denominator. So we'll have sine e to the 1 over x times e to the 1 over x, and all of this is divided by x squared. And that's our answer. So once again, we had to do the chain rule twice, because we had cosine of e to the 1 over x, but e to the 1 over x was itself a composition. Let's do a different kind of example. Suppose that f and g are differentiable at all x, but we don't know the values of f and g and their derivatives for every x. We just know it for a few. We know for x equals 1, x equals 2, and x equals 3. So for example, f evaluated at x equals 2 is 1, and g prime evaluated at x equals 3 is 9. So we don't know formulas for f or g or their derivatives, but we know their values for certain inputs, namely 1, 2, and 3. We're asked to compute certain derivatives. For example, we want to compute fg prime evaluated at 2, f divided by g prime at 3, and the composition prime at 1. So we want to use the product rule, the quotient rule, and then the chain rule to evaluate these derivatives at certain specific values. So let's go ahead and give that a try. Well, again, since we don't know what the formulas are, we can't find a formula for the derivative of the product. However, we don't need the entire formula, we just need to know it at 2. So let's just go ahead and compute this. So we're going to start with f times g prime at x. And using the product rule, this is going to be the derivative of the first times the second plus the first times the derivative of the second. Now, of course, we're interested in this not an arbitrary x, but when x is equal to 2. So let's just go ahead and plug in x equals 2. So f times g prime at x equals 2 is going to give us f prime at 2 times g at 2 plus f at 2 times g prime at 2. We don't know the general formulas for f and g, but we do know their values at 2. And that's all that we need to know. That's this row right here. So first f prime at 2, that's this one. So that's 5. And then g at 2, that's that one. So that's 8. And then f at 2 is 1. And g prime of 2, that's 7. So we end up with 5 times 8, which is 40, plus 1 times 7 is 47. Okay, so that's the product. That's the derivative of the product at 2. Next, we're asked to compute the derivative of the quotient at 3. So we start with f divided by g prime at x, and we can just use the quotient rule. So that's the derivative of the top times the bottom minus the top times the derivative of the bottom, and we're going to divide all of this by the bottom squared. And again, we don't want this at an arbitrary x, we want it at x equals 3. So we're just going to plug in x equals 3. So that will give us f over g prime at 3. We'll have f prime at 3 times g at 3 minus f at 3 times g prime at 3, and all of this is divided by g at 3 quantity squared. Now when x equals 3, that's this bottom row. So we want f prime at 3, that's 7, times g at 3, that's 2, minus f at 3 is 7, times g prime at 3 is 9, and we're going to divide that by g at 3 quantity squared, so that's 2 squared. So this is going to give us 14 minus 63 divided by 4, which is equal to minus 49 over 4. So that's our answer. So f over g, the quotient prime at 3, is equal to minus 49 over 4. All right, so that just leaves one last problem, which is this one, the composition, or rather the derivative of the composition at 1. So let's do that one next, using the chain rule. So we want to look at f composed with g prime. So f composed with g prime at x, well, that's just the derivative of the outside times the derivative of the inside. So this quantity right here, f circled g prime, that's the derivative with respect to x of f evaluated at g at x. That is to say, it's the derivative of the outside, which is f prime, evaluated at the inside, times the derivative of the inside. The derivative of the inside is g prime. Now, once again, we're interested in this at a specific value, so we want f composed with g prime at x equals 1. So that's going to give us f prime at g at 1 times g prime at 1. So we need to know what g and g prime are at 1. So we come back to our table. So g at 1 is 2 and g prime at 1 is 6. So g at 1 is 2 and g prime at 1 is 6. So this becomes f prime at 2 times 6. And what is f prime at 2? F prime at 2, that's this value right here, 5. So that tells us that this is 5. So we have 5 times 6, which is equal to 30. And that's our answer. Now at the start of this video, I claimed that the chain rule would allow us to differentiate basically any function that we encountered, and that's more or less true. We're still lacking one necessary tool, but we can use the chain rule to figure that one out. Now what do I mean? Well, let's look at this motivating example here. The derivative with respect to x of x to the x. We know how to differentiate x to a constant, and we know how to differentiate a constant to the x. But here we have x in the base and also the exponent. So how do you differentiate a thing like this? Well, the key idea is to write it in a slightly different way. We write x as e to the natural logarithm of x. So x to the x is equal to e to the ln of x raised to the x. But if you have an exponential raised to an exponent, you multiply the exponents together. So it's e to the ln of x times x. And this is the thing that we actually want to differentiate. So the derivative with respect to x of x to the x, we rewrite this as the derivative with respect to x of e to the something, like so. Now this is e to a thing, so we can use the chain rule here. Our outside function is e to the something. And what about our inside function? That's ln of x times x. So we want to use the chain rule on this composition. So our inside function is this thing right here. So the thing in the exponent. So the derivative of e to the something is e to that thing again, times the derivative of whatever was in that exponent. So we just put ln of x times x right there. So this is going to equal e to the ln of x times the derivative with respect to x of a product, which is ln of x times x. Now this first term here, this is e to the ln of x times x. We don't need to do anything with that, but e to the ln x times x was equal to x to the x to begin with. So this term, e to the ln of x times x, that's this term, which was just x to the x. So this thing right here is just x to the x. And now what about this one, this derivative? This is the derivative of a product, so we have to use the product rule. But maybe you've already spotted the difficulty. This term is equal to, we have our x to the x from the front, and then we want to do the product rule. So this is going to be equal to the derivative of the first, so it's the derivative with respect to x of ln of x. And that's our first problem, because we have no idea what that is, times the second function plus the first function times the derivative of the second function. Now, that is just the derivative of x, and that one's no problem because the derivative of x with respect to x, that's just 1. However, this term right here, we don't know what that is. But we are in a position to figure out what it is because the one thing that we need is the chain rule. Let's go to the next slide. Here it is stated as a theorem, the natural log rule. The natural logarithm is differentiable at every positive real number x, and the derivative with respect to x of the natural logarithm is 1 over x. How do we hope to show that this is true? Well, we can prove it. And the basic idea is to use something that we've already observed, namely that e to the ln of x is equal to x. That's just the cancellation rule. So what does that mean? Well, first we want to take a look at this function here, e to the ln of x. We want to differentiate that. So what is the derivative with respect to x of e to the ln of x? Well, this is e to the something. This is a composition. The derivative of e to the something is going to be e to that thing again times the derivative of that thing. Well, the derivative of that thing is ln of x. That's the thing in the exponent. Now, e to the ln of x, that's just x. So this is x. So we end up with x times the derivative with respect to x of ln of x. Now you might wonder how this helps us, because we started by computing the derivative of something, and we ended up with an x times the derivative of the natural logarithm. But the whole point of this is that we don't know what the derivative of the natural logarithm is. However, all is not lost, because this thing that we're differentiating, this is e to the ln of x, but e to the ln of x is just x. So this term, no matter how complicated it looks, this thing is just x. And this is just the derivative with respect to x of x. And we know what that is. That's equal to 1. So this is equal to 1. So that tells us that 1 is equal to x times the derivative with respect to x of ln of x. So now we just solve for the unknown quantity. Just divide everything by x, and what do we get? We get 1 over x is equal to the derivative with respect to x of ln of x. And that is exactly what we claimed. Now we can take this knowledge back to this derivative. Now what was this derivative? Let's see. If we can't remember, we can just try computing it again. So this is the derivative with respect to x of e to the ln of x raised to the x which is the derivative with respect to x of e to the ln of x times x. And then we use the chain rule. So the derivative of e to the something is e to that thing again. And then we multiply that by the derivative with respect to x of whatever was in the exponent, ln of x times x. And now we use the product rule. Well, first, let's just write this e to the ln of x. Let's just remind ourselves that this, in fact, was x to the x. So now we have x to the x times the derivative with respect to x of this product, ln of x times x. And we just want to use the product rule here. So we'll end up with x to the x times, and so it's the derivative of the first, which is the derivative of ln of x, times the second plus the first times the derivative of the second. And the derivative of the second, well, that's the derivative of x, which is 1. And the derivative of the first, that's something we now know. The derivative of logarithm is 1 over x. So we end up with x to the x times 1 over x times x plus ln of x times 1. And we can simplify this. We'll have x to the x times 1 over x times x. That's just going to give us a 1. So we'll end up with 1 plus ln of x times 1 is just ln of x. And there's our answer. So even a function as strange as x to the x, we can now differentiate now that we know the chain rule.